introduce him. Our next speaker is Ramon Nogueira. He's a postdoc at the Center for Theoretical Neuroscience at Columbia, working with Stefano Fiusi. Take it away, Ramon. Your mic is muted.
Hi, can you hear me now?
Yes.
Okay, yeah, sorry. All right, so good afternoon, and thanks for being here, and thanks for Neuromatch and Shreya and Nidhi for organizing this. So today I'm going to talk about, sorry, one second. I'm going to talk about high-dimensional neural representations for low-dimensional tasks, a compromise between complex, discrimination, and generalization. This project is a collaboration between Stefano Fiusi lab and the Randy Bruno lab at Columbia University. And importantly, all the behavioral and electrophysiological data that I'm going to present today has been collected by Chris Rogers. We already have a first manuscript of this study, which can be found on bioRxiv. I think maybe Nidhi is gonna send the link on the group chat. So what I'm going to, or I can set it afterwards. But what I'm going to present today builds up upon this first manuscript. All right, so let me start with a brief introduction. As we all have experienced, the sense of touch can be very informative about the external world. Mammals, and in particular primates, can, for instance, use their hands or limbs to identify properties of objects in their surroundings. Even though we lack an intuition for it, other animals like rodents can likewise use their whiskers to recognize their close environment and discriminate, for instance, between a solid wall or a wall with a small hole. In this study, we aim at characterizing what are the complexity properties and neural representations of whisker-based discrimination tasks. Or in other words, can the behavioral task be solved by a linear or nonlinear integration of sensory cues? And are the neural representations in the somatosensory cortex high-dimensional or low-dimensional? So in this study, head-fixed mice were trained to perform a discrimination task by whisking in the dark. By whisking in the dark. They were asked to discriminate between a concave and a convex shape by freely sampling these objects for 2 seconds. And in particular, the time course of the trial was the following. A concave or a convex shape, a convex or a concave shape, started moving towards the animal at t equals -2 seconds. And this shape would start at 3 possible distances, the far, medium, or close. And at t equals 0, the animal had to make a choice by licking on the left socket or for concave shapes and on the right socket for convex shapes. Importantly, animals were free to lick during the whole trial, but the choice at the particular trial was considered to be the first lick after this response window opened at t equals 0, right? Also, the position of these whiskers and the shape was recorded with an ultra-fast camera, and they were tracked on each time frame with DeepCatLab, which I guess many of you are or have heard about. So if you're interested in all the exact details about this particular task, check this manuscript, bioRxiv, Rogers et al. 2020. And all right, so let's have a look at the video. It's going to be much easier to get a grasp of the task in particular. For instance, we have a convex shape here. The animal is making the contacts. Also, we can have a look at what happened. Oh, sorry. Oh, sorry about that. Let's have a look at the concave shape now. Right, so now we have a concave shape. Same, animal whiskers, whisks, and the whiskers make some contacts, and which is going to be used to decide whether that was a convex or a concave shape. All right, so let's look at some behavioral results. So in this plot, we have the mean contact rate as a function of time across animals for all the whiskers. And in the beginning, where the shape is not present, is out of reach, there's no contacts, but it is between -1 and -0.5 seconds where the biggest majority, the majority of the contacts happen. And yeah, we have the different whiskers. So as I said before, animals are free to lick throughout the trial. Therefore, we can plot the probability of making a leak on the correct side as a function of time. In the beginning, when there are no contacts, the animal makes random choices, right? 50% performance. Nevertheless, once they are able to sample this sensory information by whisking, we see a performance increase. And at the end of the trial, this performance, the overall performance, is around 78%. In other words, this temporal profile indicates that mice accumulate sensory evidence through whisking, and the larger the amount of gathered information, the higher the probability of making a correct choice. All right, so the next thing that we did was to characterize the complexity of these whisker-based discrimination tasks. For each trial, we extracted a matrix that consisted of a value of different whisker features as a function of time, right? For instance, whether there was a contact or not for whisker 1, for whisker 2, for whisker 3. And then we use different classifiers, nonlinear or linear classifiers, to characterize whether in that particular trial, the stimulus was concave or convex, as well as its choice, the site that the animal licked. So we did that with different classifiers, and we got a performance of 90% and 70% performance, percent correct, respectively. And importantly, what we see here is that linear classifiers and nonlinear classifiers, multilayer perceptrons, perform equally well on the task. Or in other words, the whisker-based discrimination task can be understood as a linear integration task across space and time, where space here, I mean the different whiskers. All right, so based on this spatiotemporal pattern of whisking gathered by the animals, we created two new virtual tasks, what we call the easy and the complex task. The easy task was defined as a linear combination across whisker contacts. By construction, the easy task is a linearly separable task with respect to the whisker context. Here I'm showing a two-dimensional representation, but it is actually defined in a three-dimensional space spanned by the three whiskers that were more important. On the contrary, we also had this task, the complex task, which was defined as a nonlinear combination across whiskers. In particular, we were using an XOR, which is the most difficult nonlinear task possible. Or in a three-dimensional space, it's no longer called an XOR, it's called a parity. So by taking the same approach that we used to decode object shape and mouse choice, an insightful result was revealed, which is that linear and nonlinear classifiers all had a very similar performance on easy task, while only nonlinear classifiers performed above chance for the complex task. Therefore, these results provided further evidence that the whisker-based discrimination task is a linearly solvable integration task because we found this exact same profile. All right, so what did we do next? We wanted to analyze the neural representations of the sensory cortex and their particular properties. So while animals performed the task, populations of neurons were recorded in their barrel cortex. In order to characterize the properties of these neural representations during this task, we used an encoding approach where we fitted the firing rate of simultaneously recorded populations from all the task variables that we thought could be influencing the activity of the somatosensory cortex. Like for the behavioral case, we used different encoding models with different levels of complexity. In particular, we used a linear model that only allowed for pure and linear mixed selectivity, and a set of nonlinear models that allowed for nonlinear mixed selectivity. So what did we find? We found that the nonlinear encoding model with only one hidden layer was the model that predicted the best the activity of the population activity in the barrel cortex. And it is important to note that I am showing here the R-square on the held out data. I am not showing here the training results, the R-square for the trained set, because it would, because I don't have time, but it would basically increase. The more complex the encoding model, the better we would have our R-square. We could also evaluate the contribution of each of the different task variables on the model performance, what we call delta R-square. We saw that the number of contacts made by the whiskers and the angular position of the different whiskers were the two task variables that influenced the most the barrel cortex activity. All right, so even though we found that overall the nonlinear encoding model was better than the linear one, we found that some neurons still depicted linear mixed selectivity. Here I am showing 2 example neurons with linear mixed selectivity with respect to whisker 1 and whisker 2 and 3. We also, as expected, found neurons with nonlinear mixed selectivity. This first one example shows a sublinear mixing between C1 and C3, while this second example shows an XOR, so to speak, XOR-like tuning curve with respect to C2 and C3. All right, so I don't have a lot of time, but I will try to go fast. So until now, we have seen that the whisker-based discrimination task can be solved linearly by integration of the sensory cues sampled by the mice. But we have also seen that the neural representations of the task variables in the mouse barrel cortex are better explained by nonlinear mixed selectivity, and therefore they are high dimensional in the neural space. And then we have to ask ourselves, is this particular representation useful on a broader behavioral scheme? Well, to answer that question, to answer the question, I don't have space. Yeah. To answer the question, we used again the easy and complex task that I defined earlier in this presentation and tried to perform them by linearly reading out from the neural activity. Importantly, instead of using the raw neural activity, we use surrogate data created with the different encoding models. What we saw is that the easy task, neural activity created with the complex encoding models degraded performance on this task. On the contrary, for the complex task, only neural activity created with nonlinear encoding models had a performance different from choice. Therefore, even though the whisker-based discrimination task consists of a linear integration tasks on the whisking space, the neural representation of this task in the somatosensory cortex would allow for a complex discrimination with respect to the input variables while maintaining a good generalization properties on a simpler task. All right, so let me recap very quickly. We have seen that mice learned to perform a whisker-based discrimination task, and sensory evidence was accumulated throughout the trial by whisking. We also have seen that the shape discrimination task can be solved by linearly integrating the spatiotemporal pattern of whisking. Populations of neurons in the mouse barrel cortex show nonlinear mixed selectivity with respect to the task variables. Whisker context and angular position are the variables that explain neural activity the most. And finally, the neural representations in barrel cortex allow for complex discrimination while maintaining generalization properties in simpler tasks. Yes, and that would be it. Thank you very much.
Thanks for your talk, Ramon. So let's wait for the questions to show up. But in the meantime, I have a question for you. So your result said that, the number of contacts and the angle of the whisker, like best among the behaviors, best explain the neural activity, right?
Yes.
So have you looked at any other sort of mechanical variables, like say the stiffness, for instance? Because I've seen some work by, say, Mitra Hartman on, how mice modulate like the stiffness of their whiskers and so on. So have you tried to look at like sort of behavioral hidden variables like the stiffness?
Yes, that's a great question, very important. So as I told you, this work builds up upon a previous manuscript that has been published already. Well, it's a preprint, and in that study, I highly recommend you reading it if you're interested in this. We go through all the possible whisker variables like stiffness, curvature. Also, we were also using like task variables like previous reward, current reward, like everything that we could think of. We just put it inside, and we came up with well, you can see it there, but the variables that I used in this follow-up study were those that showed up to be the most important for behavior in the previous study. But yeah, it's a completely, it's a very important. Actually, we were surprised when we saw that the whisker curvature didn't really play a role. What really matters for behavior is the number of contacts and the angle of the whiskers, like the kind of whisking that the animal is performing. Yeah.
Cool. That's really interesting.
Yes.
Yeah. Also, could you maybe speak a bit more about, the nonlinear and the linear aspects of the model? Like you said that, linear explained some results and then nonlinear explained the other results. Could you talk more about that?
Right. So we basically used a multi-layer perceptron encoding model, right? So it's the set of task variables. I don't know why I stopped sharing, but let's do it with the hands. So it would be task variables, neural activity, and then in the middle, you can have no hidden layer, right? So this would be the linear model, or in other words, linear regression, right? But you can include a hidden layer with ReLU units, one hidden layer, two hidden layer, or three hidden layer, right? And those, when you include these hidden layers with the ReLU nonlinearity, then you're basically allowing the model to create nonlinear mixed selectivity, well, self nonlinearities, but also nonlinear mixed selectivity between the different task variables, right? And then we feed all the models with cross-validation, and we see that the multi-layer perceptron with only one hidden layer is the one that would explain best the neuronal activity.
I see. Okay, you have a question. So from Gonzalo, they ask, mice don't touch the surfaces with their whiskers simultaneously. How much temporal integration do you need to solve the task? Is there any mixed selectivity? Is any mixed selectivity good for solving the task?
Okay, so the first part of the question, if I understood correctly, is related to the temporal difference between the contact of the different whiskers. So that's an intuition that, for some reason, like every time we explain this experiment, everybody asks, well, many times we get this question, and we ourselves were expecting that result, that the temporal difference between the whisker contacts was a variable that would explain the best the behavior, but it's not true. It's not about the temporal difference between the whisker contacts, and again, I highly recommend reading this first manuscript we have, but it's the absolute number of contacts that the different whiskers make and the comparison between them. And in the beginning, we were quite surprised because that didn't make any sense to us. If you, as our intuition as humans, I don't know, here's my phone, if I want to recognize this with my hands, basically somehow I will kind of feel, or my intuition is that the difference in time between the different contacts is going to give me a mental picture of the shape that I'm touching, right? But we have very stiff and controllable devices here, but whiskers are much more like flexible and unreliable in this sense, right? So that's the explanation that we have at the moment, that it's because they are very unreliable, very flexible. They are not stiff whiskers. Relying on the temporal difference between contacts across whiskers wouldn't make much sense. So it's more about the absolute number of contacts. But again, if you want to check that, read that first manuscript. And then the second part of the question, I forgot. Can you remind me that, Nidhi, please?
Yeah, I think the second part was, is any mixed selectivity good for solving the task?
Right. So the task itself, like we have seen that there's nonlinear mixed selectivity in the barrel cortex, but for the task itself, for the whisker-based discrimination task that I just described, it wouldn't be necessary, because the task is linearly solvable. It can be solved by linearly integrating all these variables. You don't need non-linear components there. So even though we found that there is nonlinear mixed selectivity in barrel cortex, it wouldn't be necessary. But of course, the animal has been, like the somatosensory cortex has evolved in a naturalistic environment, and this is a very particular task that we are training the animals, but the cortex is optimized for a much more complex scenario in nature.
Got it. So I think we should maybe close the session now, even though there's still a question. Gonzalo says nonlinear mixed selectivity is a very broad term, but we'll have to take this offline now because we need to close the session. Thanks to all the speakers. It's been a great session with really complex real world behavior and neural recordings. So thanks to all of you.
Thank you.